Professor Clements with you as we again consider a calculation with interference and diffraction. We're talking about a double slit that has the slit opening separated by 2.5 times 10 to the minus 5 meters. Each slit has a width of 5 times 10 to the minus 6 meters. Is this possible? Yes, the slit width is smaller than the separation. They're not overlapping. It's not a complete opening. So it is a double slit situation. And this first calculation, we want to calculate 6 maxima, the first 6 maxima, the first 6 orders. Order 1 with m equals 1, order 2 with m equals 2, and so forth, as you've probably done before. We have monochromatic light, wavelength of 580 nanometers going through this double slit. So we just want to calculate the angles. I'm not going to bother calculating the y position on the screen. But if I would draw it out here, we'd have L here, we'd have Y some distance away from the central maximum, and the angle theta would be in here. But in this video, I'm not going to calculate the Y's. I'm only going to calculate the thetas. Use tangent theta to calculate the Y's if somebody tells you what the L number is. So in this situation, we're using the equation d sine theta equals m lambda. And we want to calculate 6 different thetas. Well, to save a little time, I'm going to do a side calculation here and overlap a little bit. Sine of theta is going to be m lambda over d. Only thing that's going to be changing here is the m. So I'm going to go ahead and put in the values for wavelength and d and divide those. So when I do that, I find that sine of theta is going to be m, the wavelength of 580 times 10 to the minus 9, divided by the slit separation distance, 2.5 times 10 to the minus 5. If you divide these two numbers, let me know if I'm wrong. I get m, and I have 0.0232. So we're going to be doing this 6 times, putting in different values for the m, multiplying here, and then calculating sine of theta. So I'm going to go back over to this part of my page where there's more blank space. But sine of theta is m times 0.0232. I'm going to make a table here of m, then sine theta, and then taking the inverse sine, I'll get the value for theta. When m is 1, sine theta is 0.0232. Again, putting in the value for m up here. And taking inverse sine of this number produces the theta. You should try this on your own calculator. 1.33 degrees. When m is 2, 0.0464, and 2.66 degrees. When m is 3, 0.0696, inverse sine produces 3.99. The sine function is a little bit linear, close to being linear, not perfectly linear, but I'm not putting on the extra digits here. Close to being linear when theta is small. But let's keep on going. M of 4, 0.0928, and we have 5.32. M of 5, 0.1160, and again that's 5 times this number. Tells me what sine of theta is. I take inverse sine of both sides, and for this case I get 6.66. And you can see here we're no longer strictly adding the 1.33 each time. When m is 6, 0.1392, and I have 8.00 degrees. So there's our list of angles. As m goes from 1 to 6, you should check this on your own calculator, see if you can reproduce this. That's the effect of the double slit, where we have interference. We're locating the maxima. We use the equation that locates the maxima, d sine theta equals m lambda. These are the angles where I predict there'll be a bright spot on the screen, due to the interference of light, constructive interference, from the two slits. Well, now let's switch our point of view, our calculation, to the single slits that are here. We were told the value of the width of the single slit, we'll use capital D for that. That capital D result was 5 times 10 to the minus 6. That's a given number. And we're using D sine theta equals m lambda to locate the minima locations. So again, if I solve this, sine of theta would be m lambda over d, and now we'll be taking, I believe m is a variable, 580 times 10 to the minus 9, and we're dividing by the width of a slit, 5 times 10 to the minus 6. So doing this in advance, and I come up with a way to calculate sine of theta based on m. These two numbers divide out and produce 0.116. So now it's time to go ahead and use different values of m. So first I'll use m of 1. When I do that, of course, I have 0.116 for the value of sine theta. And when I take inverse sine and do that calculation, I come up with 6.66 degrees. If I use m of 2, of course, we're going to be doubling this, 0.232. And I take inverse sine of that, and I come up with 13.4 degrees. So those are the location of the minima predicted by the single slit equation. Now, we want to comment on the results of Part A and Part B. If we look at the list of angles, notice this 6.66 minima calculation also occurs in the list of where the maxima would be located. So here we have a little bit of a paradox, easily explained, but a little bit of a paradox. The double slit calculation says we're going to have a bright spot at this angle. The single slit calculation says we'll have a minima, a dark spot on the screen. What's it going to be? It will be dark. And our situation that occurs here is that each single slit at this 6.6 degree angle is sending off 0 light. It's a minimum. Each slit sends out 0 energy at this angle. When we get to the screen out here and would consider the double slit equation that says add up what you're getting from the two slits, we can go ahead and add them up here. 0 plus 0 is dark. So 0 plus 0 at the screen. We're doing constructive interference, and what we have is called a missing order. What we have is called a missing order. Sorry about my rookie presentation. There is no light on the screen where the double slit pattern predicts a maximum. The m equals 5 is missing. We will see m equals 1, 2, 3, and 4. We'll see those bright spots. We'll see m equals 6. But at m equals 5, that angle where the double slit equation predicts a maximum, the single slit equation predicts a minimum, the single slits dominate because they're actually sending out the energy at a certain angle. We get 0 plus 0 is 0. We don't see the m equal 5 order. It's called a missing order, where we get the, we'll have a missing order anytime the angle predicted from the single slit equation is equal to the angle of the double slit equation. I'd ask you to take a look and see if you see any relationship between 2.5 times 10 to the minus 5 and 5 times 10 to the minus 6. And I'll write them down here. 2.5 times 10 to the minus 5, 5 times 10 to the minus 6. To better see how these divide, Let's change the top number to a 10 to the minus 6 power. If I make the power smaller, I have to make the number bigger. 25, 10 to the minus 6, 5 times 10 to the minus 6. The 10 to the minus 6 cancel. 25 divided by 5 is 5. So once you understand this principle, you can tell easily enough if there'll be a missing order or not. If you can divide the separation of the slits by the width of the slit and come up with an integer, a 5, you will have a missing order. It's always nice to work out the angles and see how this occurs. If this is the case of a missing order, a double slit is composed of two single slits. You must take into account the effect of the single slit pattern. It's very important in modifying the brightness of the maxima from the double slit. Keep practicing. Ask your instructor.